question as to whether or not we are alone in the universe is one that has plagued humanity for as long as we've been looking up at the night sky. Whether it be intelligent beings in a developed civilization on another planet, or the smallest microbial life living in a liquid ocean on an icy moon, irrefutable proof that life exists beyond Earth would be a cosmic game changer. This episode I spoke to biologist Wallace Arthur, who in his new book The Biological Universe estimates that the universe could be teeming with life. I got the chance to ask Wallace why he believes this is the case and what it would mean for our species.
I'm Wallace Arthur. I'm Emeritus Professor of Zoology at the National University of Ireland in Galway. And I'm by training an evolutionary biologist, but I've got very interested in the possibility, which is probably too mild a word, of extraterrestrial life and the possibility of evolution on planets other than Earth. And so I've recently published the book called The Biological Universe. It's a Cambridge University Press book. And the subtitle is Life in the Milky Way and Beyond. And so this is my attempt to combine biology, which is my own stomping ground, if you like, with astronomy in the pursuit that we tend to call these days astrobiology. But of course, astrobiology is a branch of science in its infancy because we as yet lack the evidence of extraterrestrial life, even though we are pretty sure that it exists.
Yes, and that's something that seems to come across in your writing. I mean, you're pretty sure that the universe is sort of, would you say, teeming with life, that it's just waiting to be discovered by our species?
Actually, I would, yes. I think it's almost certain that there's life out there in the universe, and not just in one place, in lots of places. I'd hazard a guess that there are probably billions of planets with life. It's kind of hard to believe because, given that we as yet don't have the evidence for it, it's hard to really feel that it's there. I mean, the way the numbers stack up, the universe is so vast, there are so many galaxies. The idea of just one tiny planet with life in a wilderness of many millions, trillions of planets without life, it doesn't seem really believable. But it's hard to feel it until we actually have the evidence. And my guess is that this life evolved, some of it evolved before us, because the universe seems to have been habitable since probably about 13 billion years ago, whereas the Earth's only about 4.5 billion years old. So probably it's been around for a long time. And then the thing is, right now, so simultaneously to what's happening here in the world, there are life forms, in my opinion, and countless planets scattered across this galaxy and others, all the way to the edge of the observable universe, and quite probably beyond that.
I think it's really interesting to think about the notion of life, and whenever you're talking about life's pretty much a high probability that it exists elsewhere in the universe. Are you talking about intelligent life, or are you mostly talking about sort of microbial life?
Well, yeah, that's an important distinction, and in fact, I guess I would classify life into three categories. So microbial, yes, that's the basic form of life, at least the basic form of life that we see around us on planet Earth. But in between that and intelligent life, there's what you might call multicellular life, multicellular but unintelligent. Okay, let's put it that way. So I'm thinking in terms of animals and plants or their equivalent on other planets. I mean, there was a book produced, it's now a couple of decades old, but quite a famous book called Rare Earth. And their idea was that microbial life might be very common, but more complex life would be exceedingly rare. Now, I happen to disagree with them. I think probably everyone reckons that complex life will be less common than microbial, and intelligent life will be less common again than ordinary animal or plant life. But that doesn't mean that the higher categories, if you like to call them that, are vanishingly rare. And so I would be surprised if, for example, there are not at least 1 trillion intelligent civilizations in the universe right now, but that might mean that there's only one in the Milky Way galaxy, whereas almost certainly our galaxy contains many, many planets with microbial life. So there's a definite sort of pecking order in the commonness of these three types of life. If you like, the higher a level of life you're looking for, the less common it's likely to be, but still in numbers terms, very common. So you can be rare as a fraction, but still extremely common as a number, if you see what I mean, because a small fraction of 1 trillion planets is still a very large number.
I think what you're talking about and your sort of analysis of the search for life, it's very optimistic. Where does that optimism come from? Like, what have you kind of based your theory on?
I suppose part of it is just the scale of the universe. Part of it is the concept of the habitable zone, which we now know quite a lot about. And having discovered now between 4,000 and 5,000 exoplanets, whereas 30 years ago we didn't know of any, we know that a fair fraction of those orbit within the habitable zone. And it seems rather unlikely that only one orbiting in the habitable zone, namely the Earth, would evolve life, and the others, despite being potentially just as habitable, somehow remain with vast oceans that are entirely sterile. It just doesn't quite ring true as an idea to me.
I think that brings us on nicely to another concept, which is what is actually needed for life to exist as we know it, and do you think there's a chance for life to exist outside of those parameters?
Yeah, that's a great question. Life as we know it, or at least broadly similar to how we know it, probably needs at least three things. First of all, it needs a source of energy. Now, we would expect that to be light energy, but on the other hand, it doesn't have to be light energy. For example, we have these crazy ecosystems around hydrothermal vents at the bottom of oceans, and those are more or less light-free systems, and those life forms make a living out of chemosynthesis rather than photosynthesis. So we know that other forms of energy can substitute for light energy. So let's say that the first requirement for life is energy, probably, but not necessarily light energy. The second requirement for life as we know it is water. And I would personally say liquid water, which is one of the many reasons I'm skeptical of the recent suggestion about life in the clouds of Venus, which of course is gaseous water. So I think we need water. That's the second thing. And the third thing is we need a small array of elements as building blocks. So at the very least, we need what you might call the famous five. We need carbon, hydrogen, nitrogen, oxygen, and phosphorus. We probably need smaller quantities of other elements too. So if you've got a source of energy, and you've got liquid water, and you've got those elements, I think that's a good starting point. And what we know is that actually you don't even have to start on the surface of a planet constructing life from square one, from just having the elements themselves, because we know that interesting organic molecules like amino acids exist in space. They exist on meteorites. They exist all over the place. So for life to start on a planet's surface, it doesn't have to go right from square one. The bits and pieces are already, in a sense, lying around on the surface of the planet, but they need to be connected together. And that's probably where things get interesting and quite difficult.
Yeah, I mean, as far as I understand it, that's sort of one of the theories of the emergence of life on Earth, isn't it? Panspermia, the fact that life could have begun beyond Earth and was then transferred to Earth. Do biologists still think that theory holds water?
Well, panspermia, certainly not. But there's a difference between what I've just described and panspermia. So the panspermia theory, which was originally the brainchild of a Swedish chemist back in the early 1900s, this proposes that actual life forms come to Earth from elsewhere. They've already evolved somewhere else. And the idea usually is that there would be some kind of hardy, resistant spores in a state of suspended animation, which, when they arrive on planet Earth, the conditions are such that they're able to reactivate themselves, reanimate themselves, if you like. Now, what I was mentioning there, the existence of amino acids in space, amino acids coming in meteorites, that's not the same thing at all, because that's the component parts of life coming in from space, or if you like, being already present in a protoplanetary disk surrounding the sun when the whole solar system was being born. So I'd say that is inevitable, whereas actual panspermia in a strict sense of spores or some kind of microbe, some kind of actual life form coming in and surviving the interstellar journey, I'd say that's probably pie in the sky.
I think it's really interesting also when you're talking about sort of the inevitability of life, and it's one of the things I always think about when you consider Earth, because obviously Earth, as we know it, is the only place that we know life to exist. So we kind of look at it as this really sort of ideal conditions for life to emerge. But I think when you think about it even deeper, you can sort of say Earth might well have existed and been and had these amiable conditions for life, but life might not ever have emerged. Do you think it was inevitable that life would emerge on Earth, or could those conditions exist without life ever actually taking hold?
I think that's probably the best question of the lot, which also means it's the hardest to answer. Yes, you can imagine 100 Earths, 100 quasi-replicates of our planet, all basking in the habitable zone, all with the right elements, all with liquid water. Now, given enough time, do they all end up evolving life? Or is it some real fluke event that happened just in one place, just on Earth? For example, maybe a bolt of lightning strikes some highly improbable collection of amino acids and other organic chemicals sitting in a little pool somewhere on the planet's surface. And if all manner of conditions hadn't been exactly as they were, that bolt of lightning would never have struck that particular assemblage of molecules and life would never have begun. You could call that, if you like, the improbable origin of life hypothesis. I don't believe that for a minute, but on the other hand, I'd be hard put to give you an explanation of why I tend to favor the opposing hypothesis, which you could call the probable life hypothesis, which is that given the right conditions on, again, we could think of 100 quasi-replicates of planet Earth, I think it would evolve on all of them, given enough time. And I mean, I suppose one way to think about it is that the surface of a planet is like a mosaic of lots and lots of patches, many of which are not suitable for the origin of life, but many of which are. And all life has to do is originate on one of them, and then, given life's capability of spreading, it can just go across the whole planet. So in the book, I call this the mosaic hypothesis, and I think It's one way of picturing what's happening on the planet's surface in the early days when there are organic molecules and there's a possibility of evolving life. But yeah, it's a really difficult question.
Just sort of staying relatively close to home in cosmic terms, do you hold out much hope for finding for our species finding life elsewhere in the solar system? I know there's like a lot of searches in the kind of subsurface oceans of icy moons like Enceladus and Europa. Do you think that those are good places to search? Do you hold out much hope?
Well, I hate to say it, but although I'm an optimist, as you've mentioned, in relation to extraterrestrial life in general, and not just in general, but in our home galaxy, the Milky Way, in terms of life in our solar system, including on those icy moons that you mentioned, I'm actually something of a pessimist. So there's a bit of a contrast here. I quite strongly suspect that there is no life in our solar system beyond the life on Earth. However, having said that, I think it's worth looking. And if I were to look anywhere, I think it is indeed in the subsurface oceans of those two moons that you mentioned, Enceladus and Europa, that I would look. And so in terms of future missions by NASA or ESA or other space organizations, I'd say if we can send a probe out there, and if in some places the ice might be thin enough to drill through and take samples of the water that we know is underneath, well, that would be absolutely fascinating to see what the results of analysis of those samples were. I still have the sneaking suspicion that it would be a negative answer, but I'd still love to see it done.
Yeah, I think that's also one of the frustrating things about thinking about life around life on planets orbiting other stars beyond their solar system, exoplanets, is that we can send probes to the bodies in our solar system, but we can't really feasibly send probes to planets orbiting other stars. But what can we actually do to search for signs of life on exoplanets?
Yeah. Now we're getting to the practicalities, and that's really important because that's how we'll find things out in the end, through practical missions of one sort and another. There is this fascinating plan, actually, to physically send a spacecraft to the nearest exoplanet, the one that's orbiting the star called Proxima Centauri, which is a mere 4 light years away. And this is the proposed project called Breakthrough Starshot, part of the broader breakthrough initiatives that were launched in 2015, I think. And the idea is to have what they call nanocraft, tiny spacecraft with light sails powered by very, very powerful lasers. And the idea is that they could maybe get up to 20% of the speed of light, and they might be able to get there in within a human lifetime and even send their radio messages back within that same lifetime. Now, that's a fascinating proposal, but I think that in less than a time it takes for a mission of that kind to deliver results, we will actually find our first evidence of life on exoplanets by other means. And so the obvious question then becomes, what other means and what are we looking for? And I think probably the single most important thing to look for, the thing that will give us the highest probability of success, is to look for biosignature gases in the atmospheres of exoplanets. And the most obvious one to look for is oxygen, along with its derivative ozone. And if we can detect exoplanets with reasonably high levels of oxygen in their atmospheres, it will be a very, very strong pointer towards the existence of extraterrestrial life, including extraterrestrial photosynthesizing life. Now, the trouble is, of course, exoplanets are incredibly distant, and They're all orbiting stars, so they're all orbiting what are for them their own local suns. And those suns are ridiculously bright compared with the planets orbiting them. Now, we want to look at the planet, and in particular, we want to look at its atmosphere. We don't want to be drowned in sunlight coming from the system concerned. And that's been quite a problem up until now. I mean, it's not been an insurmountable problem because we've had data on exoplanet atmospheres coming in since about the year 2002, I think, somewhere about then, give or take. However, our ability to look for these biosignature gases in exoplanet atmospheres will be greatly enhanced by the next generation of space telescopes, which are now at a rather advanced stage of planning. So, for example, one of these planned space projects is called HabEx. It's simply a shortened version of Habitable Exoplanets Satellite. And this is a NASA proposal which will probably either get the go-ahead or the thumbs down early next year. So we're talking about a decision quite soon. It's been in the planning for probably a decade. This and others of the same next generation of space telescopes, others like it, there's another one called LUVOIR, they operate on a different principle to the space telescopes we've had up there until now. So, for example, the Kepler Space Telescope has been our most successful exoplanet hunting device to date. And we also now have the TESS replacement of Kepler up there. But the new space telescopes are designed in a different way, and they're designed very cleverly to block out the starlight and look directly at the planet. Now, that's great because you're not talking about the planet's own light being drowned in light coming from a nearby star. But on the other hand, it carries with it its own difficulties because, of course, planets are not sources of visible light. They are, however, sources of infrared radiation, and that's actually what we're going to be concentrating on. So these new space telescopes will be able to conduct spectrographic analyses across from the visible spectrum right through a lot of the infrared, and they'll be able to detect the telltale bands which are caused by the presence of oxygen in the atmosphere. Once these new generation space telescopes get up and running, even one of them, for example, I mean, there's several on the drawing boards, but even if one of them gets up and running, then I think it's going to be a relatively short time in terms of a relatively short number of years until we detect an exoplanet with a high level of oxygen. And that's going to be the most exciting exoplanet finding yet. On top of a lot which were in themselves exciting. I mean, you can say, okay, the first proper exoplanet was probably 1995. The first Earth-like exoplanet, the one called Kepler 186f, was found in 2014, if I'm remembering correctly. The next big first will be the first one with an atmosphere that suggests the presence of life. And I'm really looking forward to that, but I hope it happens reasonably soon.
Yeah, I think it's really interesting looking back on the past, say, 3 decades of exoplanet searches, because in the early 90s it was really just it started off as like 1 or 2 exoplanets were discovered, and then it was like the floodgates opened, and now we know of thousands, and we can study them, and we can kind of confidently say that every star you see in the night sky probably has an exoplanet in orbit around it. Do you think it might be the same for the first, the discovery of life? Once we find one exoplanet with life on it, we then get better, and before we know it, we know of hundreds?
I suspect that will happen. I don't know how long it will take for that to happen. If you want to think in terms of what we might expect to find in terms of planets with life, among the exoplanets we know so far, then let's just go through a few numbers. We know of between 4,000 and 5,000 exoplanets. If there is, let's say, microbial life on, I don't know, maybe 1 in 1,000, then there's probably microbial life on 4 or 5 of the exoplanets that we've discovered so far. Now, given that animal life and then intelligent life will be rarer again, I would say that the sample of exoplanets that we have discovered to date is probably not large enough to give us yet our first planet with complex or intelligent life. But I think we'd be very unlucky if among those 4,000 or 5,000 planets, there's not at least 1 or 2 with microbes. So I would have thought that discovering our first exoplanet with microbes is possible from a practical point of view, as soon as we get the right kind of telescope up there looking for it. But discovering hundreds more replicates of that, we need to have a lot more exoplanet discoveries in general under our belt, simply because of the small fraction of them that are likely to have even just microbial life. It all comes back to this issue of big numbers versus small fractions. And so, once we've got, instead of 4,000 or 5,000 planets, 400,000 or 500,000 planets, and there'll be far more than that in the Milky Way, then we'll be talking about multiple findings of extraterrestrial life, I think, and even hopefully some which are not just microbes, but which are more interesting kinds of and more complex organisms, including maybe our first intelligent life.
I was really interested to hear about your sort of cautious skepticism regarding the phosphine in the clouds of Venus, because I think that also says a lot for the search for biosignatures in exoplanets, doesn't it? I mean, even when we find a biomarker in the atmosphere of our next door planet, it's still not clear what that means. So it becomes even more difficult, doesn't it, when you're looking at something that's, tens to hundreds of light years away?
It does become more difficult just because of the distance here, and you're quite right. However, it also potentially becomes easier. And let me explain what I mean by that, because at first it seems a bit paradoxical. But the thing is that if there's photosynthetic life on a distant exoplanet, it's quite possible that the amount of oxygen in the atmosphere could be similar to what it is here, 20%, or for example, it could be similar to what it was on Earth 1 billion or 2 billion years ago, which was a few percent, not as high as 20, but still a significant amount. The thing is that the finding of phosphine on Venus is nothing like that. We're not talking 1% at all, or even 0.1% or 1/100%. We're talking way, way, way less than 1 part per billion. 1 part per million. I think it was a few parts per billion of the Venusian atmosphere consisting of this gas called phosphine. So it is vanishingly rare. So I think that makes it a lot more difficult to interpret than it would be if you're trying to interpret a level of 10% or 20% oxygen in a planetary atmosphere. So I think that phosphine is a tricky one. It's also tricky because we know that phosphine exists in other planetary atmospheres. For example, we know that it exists in the atmosphere of Jupiter. We've known that for some time. The difficulty about the discovery of phosphine on Venus is that the atmosphere of Venus is such that it has no right to be there, if you like. It's an oxidizing atmosphere. We might expect there to be phosphates rather than phosphine. So, as the authors of that particular study rightly said, there are 2 possible explanations of this. That is, of the existence of these trace quantities that shouldn't be there. One is life, okay, so microbes floating in the clouds of Venus. But the other one is some unknown chemical process, something that we just aren't aware of yet, some way in which phosphine can be made in small quantities by a completely non-biological chemical process, even in the kind of atmosphere that Venus possesses, the so-called reducing atmosphere. So my money would be on that latter possibility. I think proposing a whole evolutionary process over billions of years to produce cloud-based microbes that can synthesize tiny quantities of phosphine, to me, it's not a terribly plausible hypothesis.
I suppose the sort of the likelihood and all the probability and the science behind it, you could really discuss and kind of go back and forth all day, really. But I suppose it's just interesting, considering if we did actually find life, be it intelligent life or microbial life, what do you think are the actual implications for our species? I suppose both from a scientific perspective, but maybe also from a philosophical perspective.
Yeah, well, I'm tempted to reply with how long have you got? But okay, I'm sure I can give a short version. I mean, obviously, the greatest impact, both scientifically and philosophically, would come from discovery of intelligent life. And that's something that's probably more likely to come through transmission of radio signals than through analysis of exoplanet atmospheres, as we've been discussing up till now. I think scientifically, if we discovered extraterrestrial intelligent life, one thing that would fascinate me would be the possibility of speeding up our scientific understanding of the universe. At the moment, we're absolutely stuck on certain key issues. For example, I could mention the notorious dark matter and dark energy, completely different from each other, completely inscrutable in both cases. I would love to hear what a more advanced civilization has made of such things. I think we would have much to learn. Now, of course, you could argue that if the intelligent extraterrestrials are not friendly, we might also have much to fear. So there's that side of it too. But with a bit of luck, they might be keener on education than on hostilities, especially given the distances involved, which means communication works okay, but physical visits and taking over our planet is probably not going to actually work in practice. So from a scientific point of view, I would just love to see our own scientific knowledge enhanced, perhaps exponentially, in a way that could take centuries to achieve without such help. Now, you might say that's cheating, but I don't know about that. I think learning from others is something that we do, and why not learn from extraterrestrial others as well as terrestrial ones? So, I mean, yes, but the broader part of your question is philosophically. And I think there, the issue is, it's kind of what we were discussing at the very beginning. The numbers and the scale of the universe are such that it's almost impossible to imagine that there isn't life out there, including intelligent life, even though it's rarer than microbial life. But actually feeling that we're not alone, as opposed to saying, well, the numbers almost dictate that we're not alone, feeling that we're not alone is harder to do without some sort of evidence. We do like to see evidence before we really believe in something, especially from a scientific perspective. And that's just as it should be. So I think the impact on our mindset of actually feeling that there's somebody else out there, as opposed to just knowing that it's logically almost necessary, that would really be quite different, and that would have spin-offs in all sorts of directions. I mean, it's interesting. I've given talks on this subject at various astronomical observatories, and you get very interesting groups of people attending such observatory events. And one thing I've noticed is that people who are, let's say, conventionally religious seem to be less likely to accept the possibility of intelligent extraterrestrial life than other people. So I don't know whether that means that we'd also have some sort of religious significance as well as more general philosophical significance. It's an area I tend as a scientist to steer clear of because it's not really amenable to scientific analysis. But I suspect that it would have all manner of philosophical implications. But for me, the single most important thing would be to replace the rather abstract, logical, we can't really be on our own here, with the actual feeling, we've just communicated with an alien intelligence. That would be just phenomenal.
Yeah, indeed, it's a mind-blowing thing to consider. Wallace, I just want to say thanks very much for speaking to me today, and good luck with the book as well. It was great speaking to you and getting your thoughts on this, I suppose, subject that we'll be debating and analysing for decades to come.
Well, thank you very much, Ian. It's been a pleasure to talk to you.